I'm going to be talking about safe operating area. We call that the SOA curve on the datasheet. Why is safe operating area important? And really, what is it about a MOSFET that influences its behavior? If we wind back and have a little introduction. Power MOSFETs can make a very versatile switch. They can operate at extreme limits. Typically, at the high end, then we can achieve DC voltages up to several hundred volts. So they can be used in low voltage applications. They can be used to control rectified AC, up to 600 or 700 volts. A low voltage MOSFET can have extremely low RDS on. We're down to about 0.5 milliohm typically in a 5x6 package, 5x6 millimeters. And in an 8x8 package, then you can be down towards 0.3, 0.35 of a milliohm, which is a phenomenal low resistance. Typically, these devices can handle 400 to 500 amps, so almost at 400 amps in a 5x6 package. In an 8x8 package, we can be up to 500 amps. And with switching speeds, certainly in the hundreds of kilohertz, getting towards a megahertz in the extreme. They're solid state, so it's a piece of silicon inside. There's no moving parts, unlike a relay or a circuit breaker or whatever. There's nothing there to wear out apart from the silicon itself. And they come in a range of different package sizes. Of course, you can get very small signal MOSFETs, but for a power device, typically from about 3 millimeters square up to the big D2 packs, which are about 10 by 16 millimeters. And a MOSFET will also withstand extreme humidity and temperature. So we're talking about temperatures from -40 to plus 175 degrees Celsius. So a MOSFET really provides the muscle to make things happen. So typically they're controlled by another piece of silicon, whether that's a custom controller, a power supply controller, or a microcontroller, is up to you. And they can achieve lots of different functions. So it could be a motor control, a speed control, could be a lighting or heating that's typically controlled with a PWM to give you some kind of proportional control. Or as a load switch, a DC load switch. So it could be protecting a battery. It could be the output switch of a USB charger, something like that. And then there's a whole load of different applications in power supply and voltage regulator. So typically AC to DC power supply or DC to DC, like a buck regulator, those kind of applications. And as you can see, you've got, the microprocessor, the intelligent bit, and you've got the MOSFET, which really is the muscle of the system. That's controlling the voltage and the current to the load, and that's what makes the cool stuff happen in your application. So if we look at a typical steady state condition for the MOSFET. So the MOSFET really is a switch. It's got two states. It can be off or it can be on. In this example, so we've chosen a 100 volt MOSFET with a voltage applied to it of 50 volts, which is about half of its total breakdown capability. So when the MOSFET's turned off, we apply 50 volts to the device, and we get a very small amount of leakage current, typically a few hundred nanoamps. So you can see in the off condition, the power will be very low, typically a few microwatts. And then if we consider the on state as well, so in the on state, we're using a MOSFET in this example that's 2 milliohms on resistance. The load current might be a few tens of amps. And you can see that because of the 2 milliohms on resistance, then you do get some power dissipated. So we've used an example there of 0.8 of a watt. But actually, we're now delivering 20 amps and 50 volts to the load, which is about a kilowatt. So that 0.8 of a watt, typically the MOSFET operates very efficiently, almost 100% efficient. But the problem occurs in the switching phase when we go from off to on or on to off. And during this period of time, we've got both current and voltage. So the current is ramping up and the voltage is ramping down. And for that brief moment in time, we have both current and voltage across the junction of the MOSFET. And you can see if we take 10 amps and 25 volts, that's 250 watts. Typically, this happens very quickly. So a few tens of nanoseconds to turn a MOSFET on or off. But in some applications, this switching time can be a lot slower. And that's what we're considering today. So if we talk about what is linear mode, a MOSFET's resistance is determined primarily by the gate voltage and by temperature. So the gate is the pin that you drive to turn the MOSFET on and off. Under ideal conditions, then, a lot of applications, typically a MOSFET will be driven at 10 volts on the gate. And at 10 volts, you can see from the graph there that with 10 volts on the gate, the device there is fully turned on. It can handle a lot of current with very low voltage across it. And that point there represents 4 milliohms in this example. So the MOSFET is fully enhanced. But when the voltage on the gate is below 10 volts, then the MOSFET behaves very differently. And we call this area that's colored orange the linear mode part of the curve. And in this area, then the MOSFET behaves like a voltage controlled resistor. And you can see a small change in the gate voltage will give you quite a significant change in the current that it can handle. Okay, so what affects a MOSFET's linear mode behavior? Well, there's two primary effects that contradict each other. The first one is that as temperature increases, the threshold voltage, the point at which the MOSFET turns on, reduces. So as the MOSFET gets hotter, the threshold gets lower. The MOSFET turns harder on or more on as the temperature increases. And then the second point is that as the temperature increases, the MOSFET's on resistance, the ODS on, also increases. So this kind of behavior causes the MOSFET to turn more off as the temperature increases. So you can see we've got two different effects. One of them is turning the MOSFET on, and the other one is turning the MOSFET off. And that's what gives you these two different curves. So if we look at the transconductance curve that should be on the data sheet for a MOSFET, you'll see this transconductance curve. And this is a plot of gate voltage versus drain current. And there's two curves there. One is at room temperature and the other one is at TJ max, which is the maximum operating temperature for that MOSFET. So if we look what happens below this point where the two curves cross, that's called the ZTC point, the zero temperature coefficient point. And that's quite an important point in working out whether the MOSFET is thermally stable or not. So below the ZTC point, imagine that the MOSFET goes into linear mode at room temperature at 25 degrees. And because of the power that you dissipate inside the device, then it starts to heat up. And as it heats up, eventually you get to the 175 degree point. So as you go from cold to hot, you get an increase in the drain current. So either the MOSFET itself will take more current, or that when you consider the cells inside the MOSFET, as they get hot, they will increase the current. Yeah. And that's what causes the MOSFET to turn harder on as the temperature increases. So if we consider the same behavior but above the ZTC point, so you can see that if we start at 25 degrees and as the MOSFET gets hotter, actually now the current reduces. So and what that means is that if you get a hot spot inside the MOSFET and as the temperature increases, actually now the hotspot is pushing the current away, and that current is going to the cooler cells. So we call this behavior thermally stable, as opposed to the previous one, which was thermally unstable. So we've got this two different behaviors then, depending on whether you operate the MOSFET above the ZTC point or below. So operating above the ZTC point, we say the device is thermally stable, and operating below the ZTC point is thermally unstable. There's another factor that comes into this, and really it's to do with how far apart the hot and cold curve are. So this difference between 25 and 175 degrees, we call that the delta I, and divide by delta T. So the di by dt is quite significant. If you've got a big di by dt, then your device is more unstable. If those curves are very close to each other, then we can say that the device is thermally stable. Okay, so looking at the gate threshold voltage, so we said that the gate threshold voltage reduces as the device gets hotter. So typically this graph goes to about 150 or 175 degrees, which is the maximum operating temperature for the MOSFET. But if you imagine those curves being extrapolated, then you can see that the threshold voltage will keep on reducing until a point where you can no longer turn the MOSFET off. So if you put enough energy into the MOSFET and you take the junction temperature beyond 175 degrees, eventually you reach a point where the MOSFET will no longer turn off. And this is one of the failure modes in some applications, because as that device gets hotter and hotter, as the cells inside get hotter, then you no longer have the ability to turn the MOSFET off, and it becomes a short circuit. So thinking about what's inside a MOSFET, as I mentioned, you've got a silicon die, and on that silicon die, there are literally thousands of trenches all arranged in parallel. And you can consider each of those trenches to be a MOSFET. In fact, the channel flows down both sides of the trench. So each trench is actually two MOSFETs. And all of these MOSFETs are connected in parallel. And that's how manufacturers achieve this incredibly low sub 1 milliohm kind of performance in a MOSFET. So depending on the external features, such as how the bond wires are connected, where the drain current comes into the device, then you get this variation in current density across the die. So not all of these cells will be exactly balanced. Where you've got wires like this on the surface, then you'll get high current density around those wires. Where you've got thermal conduction away from the silicon, so whether that's through the wire or through a copper clip, then you've got differences in the thermal mass. So areas with a low thermal mass will heat up quickly, and areas with high current density will also heat up quickly. And as we said, when those cells get hot, the threshold reduces and they start to demand a bigger share of the current. And that's where we get thermal runaway from as well. So manufacturers of MOSFETs characterize this on the data sheet, and on the data sheet you should be looking for a safe operating area graph similar to this. So let's explain what the SOA curve is about as well. So there are three areas of the SOA curve. You can see on the x-axis we've got the voltage. So this device would be a 100 volt MOSFET. So the curve is capped at 100 volts. And on the y-axis, you can see the drain current. So this horizontal line at the top of the SOA curve corresponds to the maximum drain current that this device can handle. So on this example, it's about 250 amps-ish. So the three areas of the SOA curve, you've got the line at the top there that's limited by the RDS on of the device. So there's nothing really clever about that. If you work out the amps and the volts, then that is a straight line to show the device is RDS on. Then you've got the first part of the curve, and this part of the curve is typically limited by the Z theta. That's the thermal impedance that we, as MOSFET manufacturers, we measure that in the lab with some fairly sophisticated gear, and you'll find a graph on the data sheet which has the Z theta. And then we've got the third part of the curve that's called the Spirito region. So Spirito was a clever engineer who worked out that under certain conditions, the SOA performance of a MOSFET actually falls off faster than the theory suggests. And that's because the MOSFET is operating in this unstable region, and you don't get the full entitlement. So yeah, if we look at the SOA curve, it's quoted typically for a MOSFET at 25 degrees. If you operate above 25 degrees, then you have to derate this curve. There's quite a complex formula for doing that. So you can consider the energy into the MOSFET is the current and the voltage and the time. So you've got these different curves for different time durations. You've got voltage on the x-axis, you've got current on the y-axis. So the energy into the system is current times voltage times time. The output energy is determined by the thermal impedance or the Z theta, and also the junction temperature. So assuming that you've got more energy going into the device than can get out of the device, then the MOSFET heats up. And as it heats up, as we've talked about, it becomes unstable. So the thermal stability becomes important. Yeah, the SOA curve defines how far you can operate a MOSFET before it will fail. And it's characterized by the MOSFET vendor by testing, we test about 50 devices to failure to work out where these lines on the curve should be on the data sheet. So SuperSOA is a technology invented by Nexperia to try and correct this Pareto effect. So the point at which the curve drops off faster. And the aim of SuperSOA is to give you a straight line performance and to eliminate this Pareto effect. So by various methods, we can improve the design of the silicon. We can change where the ZTC point is on that curve, and we can influence the di by dt to give you a MOSFET that is a lot more thermally stable. By clever design of the package and by using copper clip instead of bond wires, then we can improve the current spreading, and we can reduce the high density hotspots within the silicon that cause the linear mode fails. So by using a copper clip, we're adding thermal mass as well, and that's helping to reduce the Z theta. So SuperSOA promises to more or less eliminate the Pareto effects, and it's capable of delivering the best-in-class performance. One of the other things that we're doing with our SuperSOA technology is we've now started to test the SOA at both hot and cold. So typically an SOA curve is given at 25 degrees. The circles correspond to the measurement data typically that we would test in the lab, and each of these circles corresponds to a device that we've tested to destruction, and this was the last point that the device passed the test before it failed. So ideally an SOA curve, because it's safe, inherently safe, so an SOA curve should really be below these data points, because that's the last point before the device failed. When you consider the high temperature SOA, then previously you had to derate with a formula similar to this. And as you can see on the graph, when you go from 25 degrees to 125 degrees, actually you lose a lot of performance, a massive amount of performance. With SuperSOA, our as you can see from our test points, so the diamonds on the curve are actually the measured devices at 125 degrees. So what you can see is that even at 125 degrees, the SOA performance is only fallen off a little bit compared to room temperature. And so with SuperSOA, you no longer need to apply this derating. We will provide hot SOA curves on the datasheet in the future, so that as customers, you can confidently enjoy all of the benefits that SuperSOA technology brings, even at high temperature. So these two graphs side by side show the difference between a regular technology and a SuperSOA technology. So you can see a regular device is around about 4 milliohms. The SuperSOA here is around about 4.8 milliohms. So the RDS-on's gone up a bit, but also if you take off a few points on this curve, so at 50 volts and 10 milliseconds, a regular device has 2 amps, whereas a SuperSOA has 8 amps of capability. So you can see a massive difference there between the capability for these devices. So if we consider a few simple applications, we've got Hotswap, and in a Hotswap application, the device, the MOSFET is used to limit the inrush current into this load capacitor. So if you simply connect that load capacitor to the backplane, then you will get a massive inrush of current into that device. So a Hotswap application looks a little bit like this. You have a MOSFET that's driven by a Hotswap controller, and that Hotswap MOSFET has to do two things. So while the capacitor is charging up, it limits the current, and so it operates in linear mode for extended periods of time. This can be several milliseconds or more. At the end of the Hotswap cycle, then the MOSFET turns fully on, in which case it operates as a low RDS-on switch. And the idea there is you want a device with as low RDS-on as possible. The Hotswap MOSFET is a very special MOSFET. Please pay careful attention if you're designing Hotswap applications. And your Hotswap controller, so Nexperia is working with a lot of these controller designers already to provide the optimum solution for their controllers. In other applications, such as battery protection or output control, so this could be an E-fuse or it could be an output switch, then you can imagine that, with these MOSFETs being very low RDS-on, then if you've got 12 volts at the output and you've got some load capacitance, you've got very low RDS-on MOSFETs. If you apply a short circuit at the output, you can get a massive current flowing briefly through the MOSFETs. And this could coincide with, so the idea of these MOSFETs is to be able to switch off and to protect the power supply or the battery. And that means that these MOSFETs have to switch off potentially when there's hundreds or thousands of amps flowing through them. And to do that, then the SOA curve, of course, is very important. A similar application in AC to DC power supplies. So imagine an AC to DC power supply. When you plug it into the AC power, and these internal power rails are still ramping up, then it's possible to drive the MOSFET maybe in an indeterminate state. So once the power supply is up, then you're driving the MOSFET with a steady 10 volts. But during the power up or power down point, you might be driving that MOSFET with 4 or 5 volts on the gate, in which case it operates in linear mode. Similar thing again in a motor control application. It's probably relevant more for power tools and e-bikes and scooters, anything where it's possible to lock the motor. And if you've got a weak battery or a battery that's almost discharged, then maybe the battery can't sustain sufficient voltage to drive the gate of the MOSFET properly on into saturation. Then the MOSFET again might operate in linear mode with very high current. Okay.
So, Mike, how many slides do you have? Because time is running out.
Okay, I think we can probably flip through a few and just cover a few key slides. So, if looking at some different competitor devices compared to Nexperia, you can see that there is potentially a massive difference in linear mode performance. So Nexperia has some different kinds of technology that gives extremely strong linear mode performance. You can see that in the table. There's some product tables there for low voltage products that you can look at maybe afterwards. And there's a product table there that shows our high voltage, so 80 to 100 volt solution. So for those 48 volt applications, the products in gray are the products that we've had released for a while, and the products in red are what's coming in development in the next few quarters as well. Yeah, and there's a slide there really that shows in quite a lot of detail the different SOA performance versus RDS on and different package sizes. Again, the gray products are our existing portfolio, and the yellowy ones are where we're going with these products in the future. So I think at that point, maybe we'll go to questions, if that's okay. Don't know if anyone's got any questions. Ralph, I can't hear you. I can see your mouth moving.
Sorry. Now, where does an Xperia see the lower RDS on limit for 25 volt class in the future? Perhaps with chain packaging and as the package losses increase.
Yeah, sure. So in a 5x6 package, we have 0.5 milliohm. In fact, RDS on typical today we have below 0.5 milliohm. We're developing an 8x8 package where we're targeting down to about 0.3 of a milliohm. Of course, in the future, this will continue to get lower and lower.
Okay, so Mike, thank you very much for this very interesting insight, and yeah, it makes a lot of sense what you've talked about, that with the lower derating or no derating. So thank you very much for this deep insight.
My
Much
pleasure.
appreciated.
Thanks for your time, everybody. Yeah, bye-bye.